Okay, class, so let us now proceed to the second part of the topic in boiler. Okay, so by this time we are now going to discuss examples of the formulas presented in the first presentation of this topic. Okay, so let us now consider this example. The following coal has the following ultimate analysis by weight. So carbon is 70.5%, hydrogen is 4.5%, oxygen is 6%, nitrogen is 1%, sulfur is 3%, as 11%, and moisture of 4%. A Stuka-fired boiler of 195 kg per hour steaming capacity uses this coal as fuel. So calculate the volume of air in cubic meter per hour with air at 60 degrees Fahrenheit and 14.7 psi pressure. If boiler efficiency is 70% and factor of evaporation of 1.1, consider 30% excess air. Okay. So, calculate the volume of air in cubic meter per hour. So, we have here the option class for A, that is 234,019 cubic meter per hour, and for B, 215,830 cubic meter per hour, and C is 213,830 cubic meter per hour, and D, 264,830 cubic meter per hour. Okay, so here is now class the solution. Okay, so first we are going to determine the theoretical air-fuel ratio of the fuel used. Okay, so we have here the formula for the theoretical air-fuel ratio. We have the formula 11.5 multiplied by the percentage carbon plus 34.5 multiplied by hydrogen minus oxygen over 8 plus 4.29 of sulfur. Okay, since the amount of the chemicals involved in this formula are already given, so substituting now the values, so the theoretical air fuel ratio now is 9.53 kilogram of air per kilogram of fuel. So since we are given with the excess of 30%, so the actual air fuel ratio now is 9.53 multiplied by 1.3, or the actual air fuel ratio required for the complete combustion of the fuel is 12.389 kilogram of air per kilogram of fuel or coal. Okay. So, since factor of evaporation is also given, so we have the formula factor of evaporation is equal to the change in enthalpy and then divided by the HFG, of course, 2257 or 970 in English. So, the change now in enthalpy, of course, is the factor of evaporation minus 2257, or that is 2257 multiplied by 1.1, that is equal to 2,482.7 kilojoules per kilogram. And determining the heating value of the fuel, we have also the Dolong's formula. So that is 33,820 multiplied by 0.705, the percentage of carbon, plus 144,212, multiplied by the percentage of hydrogen minus percentage of oxygen over 8, plus 9304, multiplied by the sulfur content. So the heating value now is equivalent to 29,930 kilojoules per kilogram. Okay, so for the boiler efficiency of 70%, so the formula, of course, boiler efficiency is equals to the heat produced, of course, on the boiler divided by the heat supplied to the boiler. Okay, so determining now the fuel required by the boiler, so that is 0.70 multiplied by 195 steaming capacity multiplied by the change in enthalpy over MF over the heating value of the coal. So the mass of fuel required now is 23,107.56 kilogram fuel per hour. So for the mass of air required now, so mass of air, so since we have already the air fuel ratio, so mass of air now is equal to 23,000 uh, 107.56 multiplied by 12.398. So that is equivalent to 286,279.57 kilogram of air per hour. So using now the ideal gas equation, so PV is equals to MRT. And determining the volume now, so the volume required is equals to 234,019 cubic meter per hour. Okay? So that is now the answer. So the option that is of course letter A. Okay? So another class, we have also another problems here. Okay, so let us also take now this example. So 23.5 kilogram of steam per second at 5 megapascal and 400 kilopascal is produced by steam generator. The fed water enters the economizer at 145 degrees and leaves at 205. So the steam leaves the boiler drum with a quality of 98%. So the unit consume 3 kilogram of coal per second as received, having a heating value of 25,102. So kilojoules per kilogram. What would be the overall efficiency of the unit in percent? So okay, so let us now consider the properties of the steam. So at 5 megapascal and 400 degrees Celsius, the enthalpy of the steam is 3,195.7 kilojoules as obtained from the table. So again, H sub F or the enthalpy of liquid at 5 megapascal is 1154.23 kilojoules per kilogram, and H sub G or the enthalpy of the mixture is or the saturated vapor is 1640.1 kilojoules per kilogram. Okay. So at 205, so H sub F is 875, and at 145 H sub F is 610.63. Okay? So let us now solve this example. Okay? So take note that the required is of course the overall efficiency of the unit in percent. Okay? So boiler efficiency now is equals to mass of steam. Okay? Multiplied with change in enthalpy at the boiler side over the heat supplied to the boiler. So substituting values now. So the boiler efficiency is equals to 80.67%. Okay? So very easy class. Okay? Another example. So we have a waste heat recovery boiler produces 4.8 megapascal dry saturated. Okay? Steam from 104 feed water or degree Celsius feed water. The boiler receives energy from 7 kilogram per second of 954 degrees Celsius dry air. Okay? So, after passing through the waste heat boiler, the temperature of the air has been reduced to 343 degrees Celsius. So, how much steam is produced in kilogram per second? So, note, at 4.8 megapascal, dry saturated, enthalpy is 2796 kilojoules per kilogram. Okay, so we have here the option A, B, C, and D. Okay, so from approximate enthalpy of liquid, so that is H sub F is equals to the specific heat of liquid multiplied by the temperature. So that is the approximate enthalpy of the liquid. Okay, temperature multiplying by its specific heat. Okay, so the enthalpy now is 435.45 kilojoules per kilogram. Okay, heat loss is equals to heat gain. Okay, so the heat loss of course is equals to M or the mass of gas, Cp of the gas, and the change in temperature of the gas is equal to the mass of steam multiplied by the change in enthalpy of the steam. Okay, or of the steam, yes, of course, rather. Of course. Okay. So the mass of steam now required is 1.81 kilogram per seconds. Okay. So if you understand the principles involved in this topic, so it is very easy for you to solve the problem. Okay. So another. we have also another example here. So, a water tube boiler, take note, water tube boiler. So, has a capacity of 1,000 kilogram per hour of steam. The factor of evaporation 1.3. Boiler rating is 200%. Boiler efficiency is 65. Okay. Heating surface area is 0.91 square meter per boiler horsepower. So, this is rated, of course. So, and the heating value of the fuel is 18,400 kilocalories per kilogram. So, the total coal available in the bunker is 50,000 kilograms. So, determine the number of hours to consume the available fuel. Okay? So, this is very easy. Okay? So, solution now. So, we have also option here, A, B, C, and D. Okay, solution. So, knowing the factor of evaporation. Okay? So, change in enthalpy now is equals to 1.3 multiplied by 2257. So, that is 2934.1. And then getting now the formula for the boiler efficiency. So, we can easily determine the number of uh, or the mass of fuel required per hour. So, mass of fuel now is equals to 58.592 kilogram per hour. So, the time now to consume the coal inside the bunker, of course, is 50,000. So, the capacity of the bunker divided by the number of or the amount of coal required per hour. So, the time required now to consume all the boiler inside the bunker is 853.36 hours. Okay? And another example, so you are very sufficient, of course, class, with example here. So I think it is very impossible for you not to learn something about this topic. Okay, so another, two boilers are operating steadily on 91,000 kilogram of coal contained in a bunker. So one boiler is producing 1591 kilograms of steam per hour at 1.2 factor of evaporation and an efficiency of 65%. And another boiler producing 1364 kilograms of steam per hour at 1.15 factor of evaporation and an efficiency of 60%. So how many hours will the coal in the bunker run the boilers if the heating value of the coal is 759? Take note, class, that the boilers consuming the coal inside the bunker is 2. Okay, so we have the first boiler and the second boiler. So the option now is A, B, C, and D. Okay, so let us now solve for the time required. Okay, so mass of fuel for boiler 1. So since uh, there are very sufficient given, so the mass of fuel at 1, substituting values from the boiler efficiency formula. So the mass of fuel at 1 is 208.605 kilogram per hour. And the mass of fuel for boiler 2, so the same formula, of course, with different given values. Mass of fuel at 2 now is 185.673 kilogram per hour. And then computing the total fuel required per hour. Of course, that is equals to 394.278 kilogram per hour. And solving for the time to consumption of the fuel, that is the capacity, which is 91,000 divided by 394.278 uh, kilogram per hour. Okay, so that equivalent time now to consume the boiler inside the bunker is 230.8 hours. Okay, so this is very similar class to the previous example. Okay, so thank you very much, class. Okay, so that's all about my presentation for the part 2 of the boiler. Thank you very much.